Okay, we did the central tendency thing. Where's the middle? The average and the median are the usual ones. The average more often, just because we've had it longer. And this is how dispersed things are. How far away are the ends? And the main one is the standard deviation. All right, so we're going to spend a lot of time on that. But another one that is used is the range. And this is purely, what's the distance between the biggest and the smallest? Right, and this is particularly used in situations where the sample size is very small. They can't get any kind of average to mean anything. I mean, they got like 5 things. This is used in a lot of quality control work where you're working with things that you can't replicate easily. So you can't get a lot of observations. You got to deal with what you got, and they're this far apart. So that's the range. The main one is the standard deviation, and this is how far observations are from the average, except it's not a straightforward how far. We're going to go through an Excel example, and I'm going to show you the formula. This is the population standard deviation. It's got a divisor of n. This is the sample standard deviation. The divisor is n minus 1. Right. The difference is that for this, if you use this, you assume you know the population mean. Right? You're never going to know the population mean. So it's always the sample standard deviation. You may not be familiar with the formula, but look here. This is the main part. Each observation is subtracted from the average and then squared. So this is the squared difference from the average. It is literally the average squared difference. So each observation, you subtract the average and square it. That means it's always positive. Standard deviation cannot be negative. We've got numbers 2, 3, 6, and 9. That's our sample of size 4. We need the average of that. And I'm going to use the fancy one. So the average of those numbers is 5. We need the distance of each number from the average. So go to the next column, and we want to do equals number minus, and we may as well do this the official way, the average. We know it's 5. We're going to give it a cell reference. This is just more practice with Excel. Now go to in that F8, or where mine is, wherever yours is, go between the F and the 8, and we're going to lock that cell reference with a $sign. So no matter what we do from now on, this is going to keep that 5 there as part of the formula. And the difference between 2 and 5 is 3. Right? Because I'm going to square it, I don't really care what side it's on. Right? But it's on the low side, but it's 3 different. If I copy this down, the 2 is on the low side, the 3 is on the low side, 5 is 1 up, and 9 is 4 up. If I do the sum of those things, and I'm just going to run a sum, that difference will always be 0. no matter what you do, if you subtract the average from each one and add them up, it will be 0. That's the job of the average. It's in the middle. But now to calculate these things, I need to square these numbers, because I want the average squared distance. I want to make it positive, and if I do this, and you can do this with equals, click on the cell reference, and then there on the keyboard is an up arrow above the 6. I put in a 2, and I'm going to square it. So I square it, and I get a 9. That's the squared distance from the average for this number. So instead of having pieces like this, we've got squares. If I copy that down, the difference between 3 and 5 squared is only 4. This 3, because it's one more out, has more squared distance than the one that we got. Here, this is a 6. It's only 1 unit away. And I square it and I only get 1. Look what happens with the 9. The further a number is away from the average, the bigger the square is. So numbers near the middle don't matter much. Numbers out on the edges matter much more. They really contribute more because they're further away, and they contribute as the square of the distance. That's the main thing out of this formula. Add these up, and this is just going to be a sum. And the sum of the squared distances is 30. Right? The average squared distance. I got 30. I'm going to divide it by 3 instead of 4. Right? This is an artifact of statistics because I had to estimate the average. This comes into degrees of freedom that we get later on. I gave up something to estimate that average. See, I got a box of pencils and I got 5 pencils in it. You choose a pencil. How many pencils can you choose out of 5? Any one of 5. Go to there. How many pencils have I got left in the box? There's only 4. Another pencil goes out. There's only 3. At the end, there's only 1 pencil left. Here's your pencil. Choose a pencil. What have you got? It's that one or nothing. Right? That's called degrees of freedom in statistics. And when I estimate the average, I actually take 1 pencil out of the box at the start. That's where this n-1 stuff comes from. So instead of dividing by 4, I divide this by 3. If I divide this by 3, what do I get? 10, hopefully. So this is the average squared difference, taking into account the fact that I had to estimate the average. That's the real reason there's n-1. If you don't remember anything else, remember n-1. That's what we always use with samples, because we gave up something to estimate the average. This is called variance, right? And it is a fairly useless number now, because if these were in feet, if this was length in feet of something, the average is 5 feet. What is this measured in? I got the difference in feet, then what I do? I squared it. This answer is in square feet. Squared units of what I'm measuring. Right? And square feet Whoa, the variance is 10 square feet. So what? Right? For that reason, we take the square root. And this is the standard deviation. Equals SQRT, that's square root in Excel. And Excel will give you more decimals than you ever needed. And to knock off decimals easily, if you go up to the top there where it says number, there's a menu and it shows an arrow going one way and an arrow going the other. You just click on that, it knocks them off one at a time. Just rounds them. So it's just a shortcut way to do that. But now, my standard deviation is 3.2 feet. Right? The standard deviation, it actually becomes a measurement for a sample. Now my unit of measurement is a standard deviation, and it's 3.2. So if I wanted to know how far a number is from the average, I do it in terms of standard deviations. So look at the 9. The 9 was out there. How many standard deviations is 9? I'm going to divide the 9 by 3.2. This is just like converting from inches to feet. I got this many inches, I want to convert it to feet, I divide by 12. To do this in statistics, I divide by the standard deviation. That's actually why it's called standard deviation. Because I can use this to standardize everything in terms of the mean and the standard deviation. So if I divide this by 3.2, I could use the official formula. And you have to put an equal sign in front of each one. How many people got an equal sign? Yeah, I didn't. Common thing. This 9 is 2.8 standard deviations from the average. If I look at each one of these in terms of standard deviations from the average, this 6 is going to be 1 over 3.2. This 2 is going to be the minus 3. This 2 is 3 below the average, so it's basically about 1 standard deviation down. This one is 2 over 3.2. It's minus 2/3 standard deviations down. This is how I measure how different things are in a sample, is with the standard deviation. I can't stress enough that standard deviation, we get a number, but it is how we measure difference in the sample. We screw the numbers, screw the feet. We aren't interested anymore. Because we can take any sample, calculate the standard deviation, and then we can represent them all on the same basis of standard deviation. Things further from the average have more influence than things close to the average. And it's always positive. We can't have negative difference. Let's go for the fish weight for standard deviation. Fish weight for standard deviation. And there we go. I've got 3 populations of fish. Here, on this side, I have the frequency distribution. This is the frequency of the first population of fish. And I'm going to make a bar chart. And what I want to do with this is show you what standard deviation looks like. So if we go to the bottom of column A, this is population A. there's some numbers down there already. Erase those. Here, we're at the bottom. We need the average of this, and we can do this with the automatic command because we can get to the end of the list. You just click there. We're at the end of the list. Go over to the upper right where that sum sign is and tell it average. And there's the average. And we're going to knock some decimals off of this because they are completely unimportant. Now I want the standard deviation. Right? And the standard deviation command. We need an equals and then do std. And we get a list of commands that have std as the start. Our standard deviation is going to be stdev for standard deviation. And there's a couple of them here. The main ones it comes up with first is .p and .s. stdev.p assumes we know the population average. This is where our 1 degree of freedom is not lost. The one we want to use for anything is stdev.s. This is the standard deviation for a sample. That's what the .s means. And that's the one we want to use. And there's no automatic version of this. We got to do it the hard way. Just mark those numbers. There's 50 of them. Close the parentheses. And hit enter. And here, with fewer decimals, here the average is 7.7 and the standard deviation is 2.7. And these are, what was the units in here? These are inches. So where's the average here? I'm going to change this. I'm going to go select data and change the x-axis categories. And I'm going to change it to, so I got numbers that are approximately correct. Where's the average on this histogram? The average is 7.7. Puts it pretty much there. How far out is 2.7 from that average? Say it's 3 instead of 2.7. I got 7. If I go down 1 standard deviation, I go to 4. I go up 1 standard deviation, I go to 10. So here's the average. That's 1 down. That's 1 up. Look what's out here. So that this isn't a symmetric distribution at all. Right? I've got a bunch of stuff over here that my standard deviation is trying to account for, but it's more than 2 standard deviations up. That's what the standard deviation is doing. It's measuring. Another thing you can do is look at the relation between the standard deviation and the average. And this is purely how big is the standard deviation compared to the average. And to get this, you divide standard deviation by the average. And this says that the standard deviation is basically 35% of the average. That's called the coefficient of variation. And it's actually very useful, but not many people use it. And I want to look at each one of these. in Excel, I've got these formulas, and if I copy them over, they will do everything I need already. I could repeat the commands, or I can make them, copy them. This is the average for B, the average for C, standard deviation, and the coefficient of variation. Which one has the smallest coefficient of variation? C column, and they always refer to this as a percent. So this is 23%. All right, go back up, insert, bar chart, and this is population B. What's population B look like compared to population A? Look at the average. With 7.7 for A, and it is 8 for B. Standard deviation is 2.7 in A and 3 in B. They're very similar. The spread is very similar. These heights are very similar. The bulk of the distribution is here. What can I say about this distribution compared to this one in terms of the bell-shaped curve? This one's more centered, more bell-shaped. Get the third one. Insert, bar chart. This is population C. What does this one look like compared to the other two? I'm going to shrink them a little bit so I can get them all in one spot. This, in fact, is skewed. These, there's kind of a center here. There's kind of a center here. This one, they're all this way. How many big fish are there compared to small fish? A lot more big fish than small fish here. It's about equal, and they're mostly in the middle. Look at the standard deviation and the average. The average for C is 10.6, and the standard deviation is 2.4. And I haven't put the scale on them yet. This is 4, 6, 8, and so forth. So over here is the average. The thing with the standard deviation is that it is in the same units as the average, and I can use it to measure the distance of things from the average. And there's actually a name for this. It's called a z-score. And the z-score tells you how far this number is from this average in terms of the standard deviation. And I can take any two samples and calculate the z-scores so that I can compare the samples on the same basis. They're on the basis of their own standard deviation. Let's go to z-scores. I want measures of relative position. This is where things are in a sample. What we want is z-scores. And a z-score is the observation, subtract the average, and divide by the standard deviation. This is how many standard deviations is a number from the average. So if we go back to Excel, I'm going to take A. 50 observations from A, copy it, and I'm going to put it on another sheet just because. Paste it there. The average was 7.7, and the standard deviation was, what was it, 2.8? 2.7? I want to get it approximately. Yeah, 2.7. Much better. Thank you. Each of these now, I want to take the observation and subtract the average, and then divide it by standard deviation, equals, paren, the 5.2 minus 7.7. And then I want to divide that by 2.7. And we're losing accuracy in decimal places all over, but it's not going to make a lot of difference. So this is how many standard deviations 5.2 is from the average. And it is about 1 standard deviation below the average. I'm going to copy that down for the rest of them. And then remove some decimals. And here is how far each observation is from its own average in terms of its standard deviation. These are the z-scores. Distance in terms of standard deviation. So a positive z-value means it's above the average. A negative z-value means it's below the average. Calculate the average for these z-scores. Go to the bottom of the list or do equals average. Should be 0. Now we're going to do the standard deviation of the z-scores. Equals STDEV dot S paren, and then mark all the z-scores. It's 1. Because I took all of these and I standardized them, now they're all in a standard form that I can use to compare samples. Because no matter which ones of those I took, if I standardized them, I made it so that the mean is 0 and the standard deviation is 1. Basically, what I did was take the units out of it. Suppose I measure the height of people in feet or inches. And then somebody else, so somebody in Australia measures height, they're going to do it in centimeters. So now I got height in centimeters and height in feet. I can convert between those two. Or I can dump them entirely. I can take the centimeter sample, convert it with z-scores, and compare it to the inches example. And I can compare them with z-scores. I put them all on a standard basis. That's why the standard keeps coming in. This is called standardizing. And it's done with the standard deviation. That's standard deviation. And it's not just something that characterizes the sample. It's something that makes them all on the same basis, because I can measure them in terms of standard deviations. And that's the importance of that. It's not just a number. It represents a spread, a bet. And we're going to make bets based on standard deviations. All the bets are based on measurements made in standard deviations.